Hey everybody. Last video for list.v day 5. We're going to do a case study, a little bioinformatics case study. We're going to talk about DNA and translate DNA to the corresponding amino acids, the codons. So that should be fun. So let's get started. Let's define some types. We already have a type for representing a base of DNA, A, C, T, or G. A strand of DNA, we're just going to say that's a list of bases. So what we've defined here is called a type alias, which is just going to save us some literal typing, like keyboard typing. So we can just say strand to mean a list of these bases to mean some DNA. Convenient. Okay, I want to recapitulate the definition of EQ base. This is the gold star short version of EQ base. You'll notice we only have 5 cases where after we've named the cases that are true, every other case is necessarily false. So like, give it up. So this is 5 cases as opposed to the 16 you might have to deal with. And using pairs or the comma notation, either one is good. You don't have to deal with any nested matches. So that's really nice. Great. Here's a function EQ strand that lets us know whether or not 2 strands of DNA are equal. Right? It's a common enough operation to want to ask questions like this. So here, how does it work? Well, if both strands of DNA are empty, you're good to go. Right? DNA 1, DNA 2. If DNA 1 is empty, but then DNA 2 has some DNA here, there's no way they could be equal. Right? Like, how can an empty list with no bases be equal to some number of bases? And vice versa, right? If we have some DNA here and then just an empty right here, you're hosed, right? They're not going to be equal. So these 2 cases both say just false. Okay, now maybe you have like some DNA here and you have some DNA here. Okay, fine. So then we have to ask like, okay, well, for these to be equal, B1 and B2 have to be equal. So let's check that. And the rest of the DNA has to be equal. So we need to sort of make this recursive call. So and all that's equal. Okay. One other thing I want to note, Coq has decided that this function is decreasing on its first argument, but it's also decreasing on its second. Like that would be cool too. Given the choice, I think Coq always chooses sort of an earlier argument. Okay, here's a similar function that says, hey, are these 2 strands complementary? Like, does this have a T wherever that one has an A? Does this have a C wherever that one has a G, and so on? And it works a lot like EQ strand. If you look, you see the lines are almost the same. We, of course, change the recursive call. Easy mistake to make. Watch out for that one. And then we also say, okay, complement the second strand, like, I really like your shirt, or your new haircut's really lovely. And then check for equality. Now, we could have just as easily have complemented B1 and left B2 alone, because complement has this sort of like mirror property, right? If A is the complement of B, then B is the complement of A. Great. So the first exercise we want you to do is write another version of complementary, but don't explicitly do any recursion. You can call recursive functions. Don't just call this one. That's not, I know that that one already works. Call some other function to do it. Maybe you can use map and some other functions in some creative way. Think about it. That's the first one. Okay. Next, we're going to do the actual bioinformatics bit. So DNA encodes, among other things, amino acids. So 3 DNA nucleotides, 3 bases, is a single codon. So like it's going to give you an amino acid like tryptophan. Maybe you've heard people talk about turkey at Thanksgiving, where tryptophan is an amino acid in there, and people think it makes you sleepy. No, you get sleepy at Thanksgiving because you ate too much. You would have to eat like an enormous quantity of tryptophan, like you'd like poison your liver if you actually got sleepy from eating that much tryptophan. So it's a myth. Glutamine, there's like a bunch of others that like show up here, like leucine. I don't know what all of these are. There's also a special stop codon which is used in gene coding. And there's 20 of these. It's just like a thing. This is a thing that I don't always understand about biology. But like, yeah, this is it. These are the 20. And it turns out there's some like weird variants in like prokaryotes and stuff. Like, just like leave it alone. Okay, if you go to this website on Wikipedia, you'll see a table that maps every triple, every 3 DNA nucleotides, every 3 bases, into their corresponding codons. Now, okay, actually in the cell, typically it's RNA that gets encoded, which is like a different structure. We're just going to work with DNA just to keep our lives simple. Like we're just not going to actually talk about RNA at all. And this is a real thing, right? Like there are biologists who do what's called DNA genomics, where it's like don't convert to RNA, just sequence whatever you want out of the nuclear or mitochondrial DNA that's all in as like actual DNA, and work with that information directly rather than trying to talk about RNA. Anyway, look at this table. You'll see there's a lot of possibilities. So, like, how many different sequences of three bases can you have? Well, it's 4 times 4 times 4. That's 64 possibilities. In the worst case, you will have 64 cases right here. Now, it turns out you can get away with fewer, right? There'll be cases where it's like, oh, either A or C gives us this one, and G or T gives us that other one. And so you can have more concise matches, right? You can go a little bit shorter if you're careful. You have to be really methodical when writing this function. And I'm not gonna lie, programming is tedious, right? There's a lot of like, here's this information in some tabular format. Now translate it so to code that will execute that tabular format. And it's just like there's nothing to do but be careful. So like let patience and method and care and attention be your watchwords. Just like go slow. Choose some good tests. We've written a couple for you right here. 3 is not enough, right? There's 64 cases, right? We've tested a tiny, tiny bit of the program space. There should be a bunch more. So writing more here won't hurt you. Okay, so there's that function. Our last function is to say, okay, given a strand of DNA, what we'd like you to do is to translate it into a list of codons. Now, there's this problem you could have where, like, what if you had only 2 nucleotides? It's like, well, what do you do with that? There's two things you could do here. One thing you could do is you could translate it to a list of codons and then whatever leftover DNA. It's a little easier. We're just going to have you translate it to an optional list of codons. If you can do it, if it's like a multiple of 3, you should get some list of amino acids out. Here's an example that does it. But if it's not, right, we'll get none. So this will give you none, but then like so would this. Right, because there's 4, there's still that leftover A, right? This is still no good. Okay, so you'll have to write this function. Your encode function should really just be some function that sort of hunts for triples and then calls encode 1, and then you'll have to do some fancy logic to handle the possibility of this option. Okay, that's it. That's the rest of this homework. I hope you have fun writing these functions, thinking about some real things with your computer code. If you have any questions about any of this, feel free to hit me up on Zulip. I hope you don't get too bogged down in any of the biology stuff. The point here is to have it be fun. If you want to like ignore the biological meanings and just treat this as a rote exercise and that makes it easier for you, go for it. Okay, great. That's it for lists. That's all I wanted to talk about. We'll move on to day 6 coming up soon. All right, talk to y'all soon.